recording starting now. So this is June 2nd or June 1st in US time. And this is the Antrea community meeting. And for today, we will be presenting a demo of service cluster IP access performed with OVS flows, and then a demo of flow tracing. So yes, let's go ahead. Let's get started with the first demo.
Okay, thanks. And I would like to share my screen. Okay. Okay. Hello, everyone. This is Wei Qiang, and I'm going to talk about the Antrea proxy design. Okay. Here is an outline of the talk, motivations, goals, and detailed design of the Antrea proxy, and then I will do a demo about it. And at the last, I will talk about some future works of the Antrea proxy. Before we talk about motivations, I would like to introduce the current implementation about service accessing. Here are two traffic flows of service accessing. On the left side of the slide, it is the current workflow. On the right side is a workflow we expected in Antrea proxy. Considering a case, pod A is requesting the service which has only one endpoint, pod B, and the pod B is just located on the same node of pod A.
Has the slide been advanced?
Yeah.
We're not seeing the slide you're talking about, I don't believe.
I would just see the topic Antrea proxy design. So Wei Qiang.
Oh, sorry.
Okay. Mm-hmm.
Yeah. Hold on. Okay. So. Here are two traffic flows of the service accessing. On the left side of the slide is the current workflow. On the right side, it is the workflow we expected in Antrea proxy. Considering a case, pod A is requesting the service which has only one endpoint, pod B, and the pod B is just located on the same node of pod A. In current implementation, the traffic is sent from pod A to the OS, and then the OS sends the traffic to the gateway. And the gateway uses the IP tables, which is controlled by kubeproxy to find out the endpoint. And then the packet is sent back to OS and goes to pod B. And the pod B sends the response, and OS responds to the gateway, and the gateway sends the packet back to OS, and the OS sends the response to pod A. There are 8 main stages of service accessing in current implementation. And now looking at the figure right side, it looks much easier to understand for the same case by using Antrea proxy. The pod A sends a request to the OS, and the OS does the DNet and send the packet to pod B. And the pod B responds, and the OS sends a packet back to pod A. Based on this background, the OS proxy implementation could bring performance improvement and also simplify network policy processing implementation. Okay. Based on the motivations, we have 3 main goals in the first version of the Antrea proxy. First, support Kubernetes service with cluster IP, and support service session affinity, and the last support service accessing from an endpoint of the service, as known as self-access. Now, let's talk about the detail. As we mentioned before, we need to DNet the service IP to the endpoint IP. Thus, it is essential to enable NET in CT action. And for endpoint selection, we can leverage the group bucket provided by OpenFlow. For each service, we create a flow which looks like this. in table 41. It matches the service protocol, the service IP, and the service port number. Then use a group to do the endpoint selection. Each group represents endpoints of a service, and each bucket represents an endpoint. A bucket loads the IP to load service IP to rack 3 and load port number to rack 4, range from 0 to 15, and load TRACEFLOW to rack 4 as a service mark. Okay, and then the bucket sends the packet back to send the packet to table 42, where we will do endpoint DNAT. In table 42, which takes response for endpoint DNAT, each endpoint has a flow to match it. The flow matches the IP, which we stored before, and the port, and match the service flag. Okay. And then DNAT the destination IP from the service IP to the endpoint IP, and load the service city mark 21. We will not want each packet to do endpoint selection, so we should add the flow to bypass endpoint selection for packet after the first packet of connection. Here we match not the new connection and retract and match the city mark and bypass the endpoint selection in 41 and 42. Okay. Okay. For endpoint on remote node, we could use exist pipeline in table 70. For endpoint on local, we need to add flow for setting up NWDEST. Oh, sorry, not NWDEST, ETH test. Yeah. Yeah. Okay. And by organizing all these flows together, then we have the pipeline to support service cluster IP accessing. A packet goes to table 30 first. And if it is not the first packet, it will be DNATed by connection track. If the connection of the packet is not a new connection and is tracked, then it bypasses endpoint selection in table 31. In table 41, we do endpoint selection. And in table 42, we do endpoint DNAT. And in table 70 or table 71, we set up the Ethernet. We set up the Ethernet test. Table 71 or table 70. Okay. Here comes the second goals. Support service session affinity. By leveraging learn action provided in OS, we use flow to retain the endpoint selection decision. If the service enables session affinity, then its bucket would load FF1 instead of FF4. The FF1 mark means the decision needs to be learned. This bucket will also send packets back to table 41 instead of table 42. In table 41, if a service enables session affinity, there will be a learn flow with lower priority to generate flow in table 40. After learning the selection, the flow marked learning the selection, the flow marked as OX FFF4. Here is the flow generated by the learn action in table 40. Since the learn action has many limitations, for example, the learned flow cannot resubmit to a table directly. To use the set effect table, we need to modify the default flow in table 31, which let it has two actions. First, resubmit to table 40, and then resubmit to 41. And in production environment, some endpoints may be terminated, thus the learn flow would be invalid. We add this flow in table 42, which takes response for endpoint DNAT. If the service market is selected, but no endpoint could be matched, then this flow sends the packet back to table 41 to have a new endpoint selection. Okay. And in some use cases, our endpoint may request the service IP, which is supported by itself. If the OS selected itself, then the source IP and destination IP will be the same, and the import and the output of the packet would also be the same. Unfortunately, the OS will drop this kind of packets. To support self-access, we should first ensure the source IP and destination IP should not be the same. And thus in table 105, we add flows for each endpoint on current node. If the source IP and destination IP is the same, then we access the source IP to a virtual IP. In table 29, if we match self-access response packet, which has the virtual IP destination, here, then we copy the source IP to the destination IP. Later, it would hit the self-access flow. This one. Okay. As we said, the OS will drop packets if the packet is output to the port where it comes from. By using import action, we can avoid this dropping. Here are the pipeline design of the OS service accessing. And okay, now let's have a simple demo. Okay. As we can see, there are one Nginx service which type is cluster IP here, and we have two BusyBox port runs on different nodes. Right? And we want to access the service in both BusyBox port. The cluster IP. Okay, and let's see the flow. Of the master node. And here we see the session affinity flow. Yeah, the learn flow has been generated here. The idle timeout is 30 seconds. And this one, the endpoint hit it. And it should also work on the worker node. This time we dump the flow on worker node. Okay. The learn flow will also be generated, but no following connections past this flow. So we request again. Okay, I will need to investigate it later. Sorry, I need to investigate it later. Okay, next I will just show the self-access. Show self-access, so we show the test. Okay. Here we have a E2E test to ensure the self-access works. Yeah. First, we create a node. We create a pod BusyBox and set up an NC server port number 880. And then we create a service BusyBox which exposes the NC server. And then we run the command on the pod, the BusyBox pod, and try to connect to the cluster IP. And this E2E test should be passed. It takes some time. I'm guessing that there are some issues on my test bed. So, yeah, the pod isn't. The pod does not be created.
Looks like it's because kubeflow's core DNS is not ready. Maybe they are not able to access Kubernetes service because of the same error you met.
Oh, yes, that makes a problem. Sorry, so we need to skip the demo.
I think maybe we can come back to the design to see any questions, because I think this meeting we should focus on the design.
Yeah, you're right. So let's back to the design here. So guys, anyone has questions about the pipeline?
Should we try?
Oh, go ahead.
Go ahead.
Okay, just a quick question. Thanks for the walkthrough. I wanted to know if you were going to add flows to generate ICMP host unreachable or port unreachable messages when trying to access a cluster IP or a port which is not assigned to a valid service. I think kubeproxy does the same thing with IP tables. And so I wanted to check if you had a plan to do the same thing for this OVS implementation.
Yeah, I'm not gonna to do the SMP part because from the Kubernetes service spec, I think that SMP is not supposed to be supported, right?
Maybe to clarify, it's not like it's about generating a non-reachable ICMP message when somebody tries to access a port, for example, which is not a valid service port.
Yes, that's a good idea. I think it's doable, but for now, I didn't implement it.
Okay, we can come back to this later.
Yeah.
So we can just remind me, I forgot you plan to do load port or not in this machine.
No, for no port, we should still use the kubeproxy.
Okay, got it.
And Wei-Chan, this is Salvatore, and I have two questions. First, I think that we still need kubeproxy also for the host network pods. Is that correct? I don't think that we have a solution for these pods.
Host network pods. Yeah, we still need it. Yeah.
Yeah, and I mean, I really will not even know how to do that for host network pods, honestly. And then my second question is about technical documentation. So what you have here is a very interesting, but also a fairly complex design. So, now there is a lot of knowledge that will need to be shared with the other contributors. So I was wondering if you already have prepared some fairly detailed technical documentation for this.
Yeah, there's one on Google Doc. I think I could share it after this meeting.
Okay, good. Great. I don't know if we want then, the problem with Google Docs is that they are not in sync with the repo. And so they tend to kind of getting lost over time. I don't know if, and it could be a nice idea to take the parts of the Google Doc and start including them in the repository itself. I mean, this is something that we can consider.
I'm hoping
sure.
we can update the OVS pipeline documentation with the new flows and the new tables. Because for people who start working on Antrea, I think the documentation is very helpful. I mean, I'm flattering myself because I wrote it in the first place, but I think it's been helpful.
Okay, I will do.
I had a question on the pod selection when you DNAT. Do you have more details in your Google Doc about how that's done in terms of how random it is besides session affinity? And is it seeded differently every time it comes up? I'm just curious how that works as services change and such.
Maybe I should share the flow.
Or excuse me, endpoints, when endpoints come and go. Basically, how is that weighted?
Yeah.
Cody, do you mean endpoint selection, or do you mean like life cycle event?
Endpoint, well, just making sure that endpoint selection remains fairly, has a fairly equal distribution as endpoints come and go when there's a lot of endpoints involved.
Oh yeah, here is a group. the group on the BR int, yeah. And here we use a selection, use a select algorithm to select bucket. Well, the select bucket based on the weight, and we now set weight, set all bucket to weight 100. So the select should be round robin, and each bucket has the same probability to be selected.
Okay, cool.
And I think I don't know if it's interesting, but there is like PODI, but that means that we could annotate, we could support annotations for endpoints with different weights. And I don't know if that's something that IP tables. I guess they can do it in IP tables easily. I don't know.
Yeah, it's possible.
Same thing can be done. Yeah.
Okay.
Yeah. Later we may need to support topology awareness, and we can leverage the weight. Okay. Any questions, guys? Right, let's back to the slide.
Thanks, Hui-Chen.
Hello?
Yeah, I just said thanks for the presentation.
Oh yes, thank you. And here are some future works. Here are some future works first. We need to adapt to the Antrea Windows, and Wayne says she wants to replace kubeproxy on Windows totally. Yeah. And another thing is we need to support flow eviction, since we don't want too many learn flow in table 40. Yeah. And maybe we could consider support no port, yeah, just as Jianjun mentioned earlier. And we could also support endpoint slice and topology awareness, which is bring in after Kubernetes 1.17. Yeah. Okay, here that's all. And, thank you, everyone. Yeah.
Thank you very much, Wei Shang. That was a very
Great
good
work.
presentation, very informative. And I think now we can move to the next topic, which is flow tracing demonstration. I'm sorry, but I don't remember. Run, right. Go ahead.
Okay. I will introduce about the Antrea TRACEFLOW today. Okay, firstly, the TRACEFLOW is the purpose of the TRACEFLOW is to used in the network diagnostic, but Antrea currently not support this feature. This feature is used when the when there is some issue on the network. We can easily find which physical or logical module drop or running on unexpected. So this feature will make user easy to diagnose the network issue in Antrea cluster. And next is the TRACEFLOW process. The TRACEFLOW is an active method, which means user need to submit the TRACEFLOW request, and Antrea received the request and then install some OVS flows for the TRACEFLOW into all nodes. And then the Antrea will inject packets into the OVS port, which defined by the source port. When the packet travel on the open vSwitch, it will hit some flows, and some information was recorded in the OVS register. And before the packets leave or dropped by the OVS, Antrea will receive the specified packets and extract the packet information to collect the recorded data. And last, we can get all the nodes the packet pass through. And here is the implementation graph. The Antrea controller will receive the request first and do some life cycle management for this CRD. And then the TRACEFLOW module is on the Antrea agent on each node. It will receive the TRACEFLOW CRD, which managed by Antrea controller. And if the TRACEFLOW module found the source port is on it, firstly, the TRACEFLOW module will install the OpenFlow entries to the OVS on the current node. And if the TRACEFLOW module found the source port is on current node, it will also send a packet out request to OVS. After the packet leave the OVS or dropped by OVS, it will trigger a packet in requested and send the packet itself to the TRACEFLOW module back. So then the TRACEFLOW module can read the information recorded in the packet. And here is some detailed implementation. So we need to use some OVS register to record the specified information, such as drop table, output table, and the service group is not supported now, and ingress rule ID, which means conjunction ID, egress rule ID, and the tunnel destination IP. As we mentioned, we need to inject some flows before the TRACEFLOW start. The injected flows will send the packet to controller, which means Antrea agent. So it will leverage the output action instead of the original output port or the drop action. And currently we support the active method to TRACEFLOW, and the TRACEFLOW source and destination support Kubernetes pod, and the service as the TRACEFLOW destination is on the plan. But this feature rely on the Antrea proxy feature, which I just demoed. And currently we only support IP version 4, and the TCP, UDP, SMP protocol, some specified segment can be set. And also we will provide a user-friendly web interface. This interface is in progress and will be demoed. And for the TRACEFLOW result, currently we support this type of the logical node, such as spoof guard, egress, ingress, tunnel forwarding, tunnel receiving, and layer 2 forwarding. Let's start our demo. Okay, here we can see this is an Octant UI, and we can get the TRACEFLOW as a tab. Okay, we can start a new trace. We must input some information in this. This packet will be dropped because we have a network policy to restrict the destination port. So we will have the client pod and the server pod. And the network policy is to allow all egress and restrict the destination port to 80 for ingress. So we can retrieve the trace graph. Okay, we can see there is some issue on this graph, and the client pod send the packet to the spoof guard network policy egress and the forwarding to next node. And here the link is wrong. The forwarding is here. And then the ingress dropped the packet. Also, we can see the generated TRACEFLOW CRD in the second tab. To see more details, we can see the raw data here. So it's a TRACEFLOW CRD which is defined here. And the packet source destination information is filled automatically by the web UI, which users do not need to type the property. So we can say the protocol is TCP and destination TCP port, source TCP port, source pod. And here is the status which store the TRACEFLOW result here. In Antrea, we will only have 2 nodes for a packet. The first is node sender and the second is node receiver. So here is the spoof guard, egress, egress conjunction ID and the tunnel forwarding to the next node IP, and the tunnel receiving, which received the packet from Geneva tunnel. And in the ingress rule, it was dropped as expected. So we will delete this TRACEFLOW and start another one. The graph auto refresh on the UI is not supported yet, but we are working on this. So if we set the destination port to 80, all the traces are okay. Okay, we can also TRACEFLOW on one node, which only contains the node sender. Okay. On one node, it was dropped by the network policy ingress. And if the destination port is 80, all the packet are delivered. And we can see the detailed information here. So we only have the node sender here, and it is delivered. Here is the documentations for this feature, the proposal, and the Google Doc. Okay, any questions?
Just a simple curiosity on my side. This is Salvatore, and I noticed that you're reporting the rule ID that when when an ingress rule is accepted. But is there any way to map that rule ID to a specific Kubernetes network policy?
Yes, we are still on work in progress on this feature.
Okay, thanks.
But we can only store the rule ID here. So maybe we need to set another query to map the conjunction ID back to the network policy ID.
Makes sense.
Hi, Ryan. This is Victor. Hello, Ran.
Hello.
Hi, this is Srikar. I have a question regarding the support for pod to cluster IP, pod to service. Do you support TRACEFLOW?
For service IP, it is not supported yet because we must implement the Antrea proxy feature first.
Oh, okay, sure. Okay. Okay.
Okay, we can see, we also can see the deployed OVS flows here. We set the hard timeout to 300 seconds for the TRACEFLOW use. Any other questions?
Are trace flows all executed single threaded? The reason I ask, I saw you were using some registers to store information. What happens if multiple trace flows with the same common endpoint are started? Will that cause any issues or?
We support run TRACEFLOW because we will use the registers to store the TRACEFLOW IDs. So as we see here, this is the cross node tag. This is the ID to identify the TRACEFLOW running at the same time. We will use 4 bits to store this ID. So at most, we can support the 15 TRACEFLOW running in parallel.
Would TRACEFLOW be a attack vector for a DOS?
Currently, it is not supported.
And I know we're still in the prototype. I was just thinking a little further ahead. Did the question make sense to everyone? I'm not sure. I'm asking if
It
basically
probably
denial of
does.
service.
Yeah.
Could you use the TRACEFLOW for denial of service, right?
I mean, you could use TRACEFLOW to generate denial of service, right? That's your question.
Right. That's my question. Yes.
Yeah. Yeah, I guess that if we don't have some sort of rate limiting on TRACEFLOW requests on the Antrea controller, yes, we could probably saturate the. What do you reckon, Ran?
Okay. Just something else that we'll need to think about from an RBAC perspective at some point, and rate limiting as well.
So you mean the rate limit, right?
Right.
As I mentioned before, we only have the 4 bits to store the ID, so we can only have no more than 15 TRACEFLOWs running at the same time. So it is the limit.
Okay.
Sounds good.
Okay, anyone else? Okay, thank you.
Okay, thanks a lot, Ran. And so this pretty much concludes everything that we had in the agenda for today. Is there any other topic that you would like to bring up for today?
One of the things that we would like to do possibly for the next meeting is set aside time for kind of an ask me anything, or to encourage new users to the project to be able to come in and maybe learn something about the project. And I think that maybe we could set aside like 10 or 15 minutes in our next meeting to have kind of as an open forum for new users if they want to come ask questions.
Yes, that makes sense. That's a good idea. I don't think that we still we yet have a user and developer community large enough to grant, you know, like doing town halls meetings or stuff like that. So it's good to have like 15 minutes for every community meeting. It seems like a good idea. Okay, so thanks, Cody, for bringing this up. So we'll make sure to leave at least 15 minutes aside when scheduling, preparing the agenda for the next meeting. Is there anything else that we would like to discuss for today? Okay, it seems that it might be all. So I'm just leaving you 5 more seconds, 10 more seconds if you want to bring any other topic, and otherwise it will be goodbye for today. Perfect. So it appears that there is nothing else worth discussing for today. So thank you very much for attending. Special thanks to Wei Chang and Ran for the great demos that we had today. And these two new features are really going to make a huge impact on Antrea. So I cannot wait to see them deployed in production. So thank you very much for attending. And with this, we can stop the recording and conclude today's meeting.